Hello, this is Wenfeng Wan from Stony Brook University, New York State, USA. So our title is DA-AFM for Ultra PV and Wind Energy Integration. So first, I want to explain some about the name. DA-AFM is a method we proposed. DA it means distributed and asynchronous. So it's the computation method of our method. So AFM is active fault management. It means it relates to the function of our method. So these three researchers in the bottom of this slide are the co-authors of this paper. The motivation, the first motivation is the increasing adoption of hybrid wind solar projects, such as the Helena Energy Center in southern Texas, and also the electrical system of London, UK, which is connected to many PV farms and wind farms. The second motivation is DA-FIG-based wind farms are prone to cloudbar activation after disturbances. So cloudbar is widely used to protect DA-FIG when fault happens. So when cloudbar is activated, large currents will be diverted to cloudbar instead of converters. In this way, cloudbar can protect the rotors from overcurrents. However, when cloudbar is activated, DFIG would lose controllability, and also it will absorb large amount of reactive power from the grid, which is not good for the grid recovery. So this paper's work is to control renewable generation during electrical faults. There are two contributions. The first one is leveraging PV farms interface converters to smooth voltage drops so that cloudbars equipped in DFIG-based wind farms will not be activated. In this way, DFIG can output some amount of reactive power to support the main grid's recovery. The second one contribution is a distributed and asynchronous surrogate Lagrangian relaxation method is devised to coordinate various PV farms of different types. The method we proposed, the DA-AFM, distributed and asynchronous active fault management for PV farms and wind farms, has two stages. The first one is called a voltage smooth stage. It spans from, it happens immediately after fault happens and lasts for about 20 milliseconds. The second stage, PV farms coordination stage, it spans from the end of the first stage until the fault is cleared. The left picture shows the one-line diagram of our simulated system. So two PV farms and one wind farms are connected to the same point of connection and then connected to the main grid by a transformer. The main grid, the fault happens in the main grid. The right picture shows the rationale of DA-AFM's first stage, voltage smooth stage. There are three lines. The red line is the grid voltages after fault happens. It will drop very quickly. The first line, line 1, the green line, is the voltages we want the PV farms to output. So if the voltages is similar to the green line 1, it means the voltages drop slowly. So if wind farms experience this slowly changing voltages, the cloudbar in DFIG will not be activated. For the case study, we studied the three-phase to ground fault. It happens at 0.4 seconds. So from 0.4 seconds to 0.42 seconds is voltage smooth stage, and after 0.42 seconds is PV farm's coordination stage. So the right picture shows voltages at fault location and also voltages at the PV farm's connection point. So as you can see, when fault happens after 0.4 seconds, the voltages at the fault location drop immediately, while the PV farm's output voltages will drop slowly. So in this way, the window farm will experience slowly changing voltages, and thus its clock bar will not be activated. In conclusion, so we have finished first, we have designed distributed and asynchronous active fault management for PV and wind energy integration. It can enable renewable generators to run through faults and also provide ancillary services to the main grid. DA-AFM has two stages, voltage buffer stage and PV farms coordination stage. In the future, we want to verify our method with real-time simulation. And we want to extend the number of PV farms to thousands of PV farms. And we also want to integrate our method with electrical vehicles facility, such as charging stations